Hello everyone and welcome to today's AusMine webinar, Data-Driven Maintenance Decisions, What We Learned from Global Deployments in Coal Operations by Razor Labs. My name is Sam Sakasiris. I'm the National Membership Team Leader here at AusMine. Before we begin, I would like to acknowledge that I'm hosting this webinar from the lands of the Whadjuk Noongar people. I also acknowledge the traditional custodians of the various lands on which we all work today and the Aboriginal and Torres Strait Islander people that may be attending this webinar. I'm joined today by two people from Razor Labs, Michael Zolotov, Co-Founder and Chief Technology Officer, and Andrew Korshall, Vice President Sales Australia. Across multiple sites in the coal sector, Razor Labs has partnered with leading mining companies to deploy DataMind AI, their AI-powered predictive maintenance platform. In this webinar, they'll share key lessons and results from deployments across various coal operations, covering critical equipment such as compressors, conveyors, pumps, and centrifuges. As we would like this to be an interactive discussion, please submit your questions as we go. They're at the bottom of the screen. At the end of the presentation, Michael or Andrew will respond accordingly. This is a great opportunity to receive expert insights on the topics covered. So you can send through your questions anytime. You can also upvote on other audience questions that you most want answered. We will try to get it to as many of the questions as we can in the time that we have. We are recording this webinar and we'll make it available to all attendees with a link to the AusMine YouTube channel in the coming days. So with all that said, I'd like now to hand over to Andrew to commence the discussion.
Thanks for that, Sam. Welcome everyone, and thank you for joining today's webinar. I'm Andrew Korshall, VP of Sales at Razor Labs. We are proud to be leaders in predictive maintenance, particularly in the mining space. I have spent a big part of my career working with the sites across Australia and Southeast Asia, working with everything from iron ore to coal and everything in between. So I have seen firsthand the challenges and opportunities within the mining industry. Today, we are talking about something that is already making a significant shift in how mining operations approach maintenance. All-in-one DataMind AI system based on the cutting-edge sensor fusion technology, which is transforming the way mining companies manage assets, identifying potential failures, and improve operational efficiency, especially in the coal sector. With me today is Michael, our Chief Technology Officer, and one of the key minds behind this groundbreaking technology. Michael is a serial entrepreneur and has led multiple companies through acquisitions and IPO. He also played a crucial role in driving Razor Labs' global expansion. Michael is an expert in radar technology, AI, and analytics, and holds a master's degree in specializing in deep learning for medical applications. Michael, great to have you here today.
Thank you very much, Andrew. Thank you, Andrew, and thank you, Sam, for the introduction and for the opportunity. So friends, I'd like to take this webinar to really walk you through some of our experiences and case studies in coal. Feel free during the presentation to just send out your questions. I'll answer to everything, I promise, and we can just take it forward together.
Sure. So now, thanks for that. And now on to the main topic of the webinar. Across the multiple sites in the coal sector, Razor Labs has partnered with leading mining companies to deploy DataMind AI, our AI-powered predictive maintenance platform. During this session, we're going to share the key lessons and results from those deployments, covering critical equipments like centrifuge, conveyors, and pumps. In today's presentation, we'll show you the real-world case studies. We highlight how DataMind AI has identified the early-stage faults that traditional condition monitoring often miss, help coal sites significantly reduce unplanned downtime to avoid costly maintenance and production losses, and enhance workforce safety by eliminating the needs for hazards for manual inspection. We'll also dive into how major coal producers are leveraging AI sensor fusion, combining the data from vibrations, temperatures, pressures, current, oil, and visual sensors to shift from reactive maintenance to predictive maintenance. This transformation is improving asset reliability and driving operational efficiency at scale. Michael, I'm really excited to hear your insights and take everyone through the journey of how AI is making a real impact in the coal industry. Over to you.
Thank you very much, Andrew. Thank you for the introduction. We have a lot of experience with different coal sites. You can see on the screen here some of the geographies, whether it's in Australia, in Africa, North America, and Latin America. And I guess it's amazing to see the huge diversity, both of the KPIs and the challenges and the solutions to them. And we'll try in this webinar to really share some of the findings and some of the lessons that we learned from all of these deployments. As Andrew said, we are in the business of predicting health of equipment. We do it both in fixed assets and mobile fleet. In this webinar, we're going to concentrate on the fixed assets. We can speak about the mobile fleet in the next webinar. And what is amazing to see is the difference in the KPIs between sites. From underground sites that are, let me use also the laser here, from underground sites that are really looking to just push more tons, to plants and CHPPs that are really looking at reducing their maintenance costs and reducing their spare parts and replacements. KPIs are very different from one site to another. And when we actually engage with the site, I hope that we have the time to speak about that as well. Understanding what are the KPIs of the site is critical when choosing the right equipment to monitor. We also see, obviously, in the last year, because of the reduction of the coal prices, that looking at the reduction of the maintenance costs is more important than ever. And I would say that this is one of the critical KPIs that sites are looking for today. What I want is to start with one example, and we can just go from there. And the example is on the reduction of the, and the example is on the increase of the productivity. One of the maybe key places where this can be done is by looking at the run-of-mine conveyors. And these run-of-mine conveyors are one of the key places where many times reducing the unplanned downtime is really directly translating to increase of tons and increase of productivity, because many times they are actually the bottleneck. And in this case, we're actually using AI vision with deep learning to analyze various patterns in the cameras. We're going to show you here some of the examples and also going to dive deeper into some of them. And actually, when we started working in this one, this is one of the lessons that we learned. We actually started by trending these phenomena. And what we're going to speak about later is that many sites in the last year actually asked us to go ahead and actually integrate to their controls to also stop the conveyor in critical cases, also preventing catastrophes. We're going to also speak about this one. What you see now on the screen is some of the phenomena that can be found by analyzing conveyors in real time. One of the critical ones is out of spec ore. You can see here how this one looks in coal specifically. This is the raw data on the left side, and the ore sizing that is done in real time on the right side. I've put here just a section of that conveyor so it's clear the differences. And what you can basically see is that each rock, despite being, black on black, is measured exactly, and the measurement is done precisely in millimeters. And this allows us to really monitor oversized ore that might cause damage downstream and might cause downstream both blockages and stoppages because of overload. Second phenomena is misalignment and tracking issues of the belt. And then we have volume variations, blockages, and basically rips of the belt. The rips of the belt can be seen from various angles. Here you can see a rip on the left side, but we're also going to discuss other methods of detecting rip belts in real time. In addition to that, we're able to place cameras right after the shoots and monitor the condition of belt clips and splices. You can see them here on the screen, how different health conditions of clips, and basically in this case, clips, are visible between yellow, orange, and red. And you can see, obviously, clips are placed as a temporary solution. One of the lessons that we learned from sites is that sometimes this temporary solution becomes kind of a permanent one, obviously, in some sites. And these ones actually deteriorate and cause rips. And by putting a camera, we're able to classify the condition of the clips to different categories and to give early warning before these ones completely deteriorate and cause rips of the belts. When I look at the oversized ore, when I look at the monitoring of it in real time and trending, basically what we're doing is we're extracting a real-time particle size distribution. And this particle size distribution allows us, because we know what is the either crusher gap or the sizer gap, we know what the ore size should be, and we're able to trend and track the oversized. And it means that these measurements of ore becomes basically a trend, that when it becomes too large, right, when we see it trending to the yellow and orange spaces, we're able to actually issue an alert, whether it's in SMS messages and emails, to the team on site. And then the team on site can actually go ahead and either calibrate their crusher gap if it's in the discharge of crushers, or make sure there are no holes in the screens, and so on, and basically prevent stoppages downstream. Similarly, we're doing to imbalance of belts and tracking issues. You can see that we're actually monitoring the distance between the tips of the belts and the tips of the rollers. You can see it here on the right side. And when this distance becomes too small, then this is measured in millimeters, we're able to issue an alert. Now, as I said, when we started working with sites, these were solutions that were looking at the current statistics, let's say the last few hours, creating these trends, and then usually you could see deterioration, let's say in these cases, a few days before it becomes too late, which gives the site plenty of time to react. One of the lessons that was that there are critical cases. For example, when the tracking issue is really extreme, or when we have a, let's say, 500-millimeter boulder that is going through the process. And in these cases, sites actually asked us to integrate to their controls. It can be done very easily with very popular protocols like OPC UA. And that camera actually performs all the processing on-prem, on the spot in real time. The data does not need to be sent to the cloud, which obviously takes more time. And whether it's a major rip of the belt, whether it's a very large boulder and so on, it can actually send a SCADA signal. We're basically creating a new SCADA tag that the team on site can choose to stop their conveyors. And that was a major lesson that we learned in the last year. Another lesson in this case was also the ability to detect rips of the belt, where we've seen in some sites that they actually cause the belt to fold. So the rip is formed under the material. It cannot be seen because the material is obviously covering it. But when it becomes a bit larger, it actually, in some cases, makes the belt fold in two. And because here, as you see, we're measuring the width of the belt, we see dramatic reduction in the width very, very quickly. And that is able to, again, trigger this stoppage. And we're both implementing this one in underground mines and in run-of-mine conveyors. And because, again, this is many times a bottleneck, because this is the feed to the plant, this actually has a direct translation to increase of productivity and tonnage, and obviously increased revenues of the site. This is usually one of the key places that we start discussions with the sites, because this is also where the business case that we're going to speak about and elaborate more about is one of the strongest ones. Looking at the run-of-mine conveyors, looking at the plant conveyors. Also looking at the oversized. Another lesson that was learned is that when it is dramatic oversized, it actually leads to blockages. And when we look at past downtime of the last few years of different coal plants, we actually see that blockages are one of the largest criteria of downtime. When we actually look at the factors of downtime, in some sites, blockages are among the largest factors. And by preventing these oversized ore, and even placing cameras that look directly at the chutes and are able to find these blockages directly, we're able to reduce the amount of these blockages, and again, directly impact the productivity of the site. But now I want to also discuss some of the other metrics here. We discussed the productivity. I want to discuss the maintenance costs, which are, again, one of the leading metrics in this year's, let's say, discussions, because when the coal prices go down, sites are looking at how can I operate the same way, but with lower costs, either per hour, per ton, per year, and so on. And one of the key KPIs that we're looking at is the ability to prolong equipment life, right? To really push replacement of major components like critical motors and gearboxes and so on to later times by delivering online condition monitoring to these ones. So we discussed conveyors, but we only discussed the visual aspect and the belts. Now I want to look at the rest of the conveyor and the drive system. And the way that we monitor these ones is, you can see here the drive system, you can see here the motor on the left side, connected to the coupling and then connected to the gearbox. And in these cases, we're putting both vibration sensors on the entire drive, right, from the motor to the gearbox. We're also putting an oil sensor, which is pretty unique. It's an online oil sensor that allows us to monitor the oil condition in real time. And also combining this one, Andrew was speaking about AI sensor fusion and combination of parameters. So we're combining this one together with the tachometer, the speed measurement, and the motor current. And what we want to show here is one of the deployments that we've done in our call site in Australia. And actually, after the deployment, the system picked up on fluting of the bearing. And you can see here one of the screens of the diagnosis of the system. You can see that unlike, I hope that you can also see my mouse, but unlike, let's say, simplistic thresholds that just tell you a temperature here is above 70 or a pressure here dropped below 50, here it's a much more profound diagnosis. It actually says that there is not only a bearing issue, but this is a fluting issue of the bearing. Fluting is a phenomena where electrical current goes through the bearing and shortens the bearing life. Now, it's very easy to find deterioration of bearings, right? Any vibration system can do it. But the problem here is that even if you replace the bearing and you put a new bearing instead, the fluting, meaning the current that goes through the bearing, will just continue because the root cause was not resolved. And the new bearing will have also shortened life, and so on and so on. So the site keeps on replacing bearings after bearings with higher frequency than they should. And obviously, all the energy that goes into that, the costs, the labor, and so on, are much higher than they should be. And in this case, our system is actually using an algorithm called envelope demodulation. On the left side, you see a regular spectrum. A vibration analyst will look at the spectrum and we'll see that obviously we have here the bearing frequencies, but the fluting cannot be seen. So in this case, in regular vibration analysis, they will just replace the bearing, and the new bearing, as I said, will suffer from the same root cause, from the same issue. But when you perform envelope demodulation, you're actually able to see here these specific frequencies that indicate, electrical issues. It can be seen in the side lobes of the main bearing frequency. The side lobes will be in the electrical frequencies. It is impossible, almost impossible to see it in the regular frequency, but here it can be seen. And therefore, the system didn't just tell the site that they need to replace the bearing, but they told them that there is a grounding issue there. The grounding needs to be checked and repaired, and that prevents the floating issue, which really prolongs the equipment life. And the life of the bearing can be really doubled by stopping the floating. So imagine it's not only that bearing, but all the future bearings that now their life has nearly doubled. And obviously less replacement, meaning for the same operation, same throughput, same everything, really the same, really lower maintenance costs. How does this one work? Okay, and how does what Andrew said about AI sensor fusion come into place here? So Andrew was speaking about sensor fusion, and I want to speak now about how this one is applicable specifically to this case. One of the problems with mining is that the equipment is very noisy, right? Whether it's a crusher or a sizer or a mill or a conveyor, by definition, because of the material, there is dramatically more noise in the system than the tiny noise that is generated by a small bearing or a gear. And because this noise is so high, it is very hard to see very subtle phenomena, such as the fluting example that I've just given right now, because the noise is just much higher than these tiny patterns. And the AI sensor fusion, along with these very sophisticated algorithms, allow us to dramatically reduce the noise and then these phenomena can be seen. How do we do it? We do it in two stages. First of all, there are very large variations in any mining operation. Now there is more ore. A minute ago we had less ore. The rocks are larger, they're smaller. All of that induces a lot of noise and does not allow us to see the real phenomena. The analogy here is that if you take your car and you drive it on a mountain, obviously the engine of the car is now working harder, right? And obviously it's vibrating stronger. It doesn't mean that there's something wrong with the car, it's just working stronger. So these operational variations are creating a lot of noise that is preventing us from seeing what is interesting for us. But because we have now the motor current, which is a measure of the load of the system, and because we have the tachometer, that is a measure of the speed of the system, we're able to, and we're online monitoring, right? We're looking at second after second. We're able to only track moments which have exactly the same load and exactly the same speed. And this dramatically reduces the noise of the operational variations because we just always look at the same operational conditions. And that dramatically reduces the noise. The second is that the system comes pre-equipped with the understanding and the knowledge of what frequencies actually matter. For example, here it knew exactly what is the fluting frequency and where it needs to look. 99% of the frequencies are really irrelevant for for condition monitoring. But when we're able to completely remove them and only focus on the ones that are actually critical for a specific failure, this allows us to again to remove dramatically the noise that is in irrelevant frequencies and only to be left in the signal of the relevant frequencies, reducing also the operational variations, and then we're left with this beautiful signal that really allows us to perform very profound diagnosis. You can already see the difference between this system and other systems. We do not look at vibration alone. We've seen cameras, we've seen motor current and tachometer all put together, just in this case of the conveyors, but also the ability to not transfer the workload of identifying what should be the threshold of every frequency to the site, which many systems do. This system comes already pre-equipped with the knowledge of what needs to be looked at and what is the right way to perform diagnosis. And especially, it's basically a recommendation system to the site experts. Obviously, they have full access to the data and they can tweak it and look at whatever they want. But it already comes with the recommendations of what it found for their specific inspection onwards. So this is a bit under the hood about how the system works. Another thing that the system does is after maintenance is actually performed, because we're able to see the work orders and we're able to see the maintenance that is actually performed on site, we're able to actually verify this one. We're able to see, okay, I've seen that specific pattern, in this case, fluting. The site team corrected the grounding, they replaced the bearing. We now have a new bearing with no fluting. I'm able to see a very dramatic reduction in these relevant frequencies back to normal, and now the system can become green again. So it's not only diagnosing what is wrong and how severe it is, but also the ability to verify the maintenance. When I'm able, so now you kind of have an initial intuition of AI sensor fusion and how do we use it. And I would like to go maybe a step deeper into that. So what systems are even used in the first place? So we gave here the example of sensors. We discussed different sensors. I'm gonna also go a bit deeper into this one. But we're also using oil analysis that is performed on site in laboratory reports. It is actually also ingested automatically and analyzed by the system along with the other sensors. We're looking at the maintenance data. So in this case, as I said, being able to verify that the maintenance was correct. I'm going to give another example in the next use case. And as I said, we're not only monitoring fixed assets, we're also monitoring mobile fleets, which are a completely different subject for another webinar. And in this case, we're also looking at tire information because tires are very expensive. And the ability to prolong tire lifespan is a critical KPI in many sites. And obviously dispatch information, because one of the capabilities is also to detect both mechanical abuse and operator abuse of these, whether haul trucks and excavators and so on. And it is also a key part of the system. So all of these data sources are ingested together, but more importantly, are analyzed together in the diagnosis that is performed. Basically, just like a doctor looks together at CT and MRI and blood work and combines all of them in the diagnosis, the system does the same. And when I actually look at the sensors themselves under the sensor category, so we discussed cameras, we looked at out-of-spec ore, we looked at belt misalignment, we looked at belt trips. These are phenomena that cannot be identified by any other sensor. And we're gonna also show flotation cells in this category. We looked at how do we combine vibration with motor current and tachometers in order to identify mechanical deteriorations and to perform root cause analysis that is really reducing directly maintenance costs. Pressure and flow, we're gonna also mention this one regarding pumps. Looking at pump curves allows us to monitor phenomena that cannot be seen in vibration. And obviously oil analysis, which can be a completely different subject, both used in mobile fleet and fixed assets that allow us to capture oil contamination, oil leaks, and other phenomena in the oil much earlier, because obviously normally laboratory reports are only done, let's say, at least once a month. So to sum up, we looked at both conveyors from a camera perspective, both from a camera perspective and from a mechanical perspective. Another thing that I want to mention before we move to the next example, I hope that this one, let's see if I can play this one. So another example is the ability to actually monitor bubble sizes, bubble colors in flotation cells. These ones are used in coal as well in Australia and other geographies, along with their usage obviously in copper and gold sites. But now I want to also look at the maintenance cost through a different case study and a very different root cause of the failure that was found there. And I want to speak about a use case that we had in coal centrifuges in one of the plants. So monitoring of a centrifuge is pretty similar in this case to monitoring the drive of a conveyor. We're putting vibration sensors along the bearings of the centrifuge and the motor. And we're also, just like in the other case, we're fusing this one with the motor current and the tachometer, again, for the same operation mode and the noise reduction that is required here. And what actually happened on this site is that this centrifuge was completely healthy. And because we're integrated again to the maintenance tasks through SAP, we're able to see that they performed the maintenance, and actually after the maintenance, it became orange. So the maintenance itself actually induced deterioration of the centrifuge. And what we've seen after the maintenance is that there was a very severe imbalance of the drum itself. And the system diagnosis here was that it was probably, you can see here in the English text, it's probably accumulation of debris and basically residue in the centrifuge. One of the common things to do after a long maintenance of a centrifuge is to clean that residue that otherwise just stays there and leads to this severe imbalance. And another thing that it leads to is a dramatically, obviously, lower efficiency of the centrifuge. Because it is filled, obviously it's not able to perform its job as efficiently. And the recommendation here was to, first of all, inspect the drum, as you can see here on the screen, for that residue. And after it is removed, obviously to perform balancing of the centrifuge back. You can see here what the system saw under the hood. So after it removed, after it performed this operation mode isolation and removed the other frequencies, you can see, let me use here the laser, that after that maintenance that was performed here when it was not working, the levels of these relevant frequencies increased almost by 3 times. And the system was literally able to pick it up the day after and perform that deep diagnosis of what exactly needs to be done. The team on site went over the results. They went to the centrifuge. They did find the same residue, and they obviously removed it and they balanced it. and you can see how quickly was the reaction. Now, you can see that from the moment that we identified this one to the full resolution of this issue was less than 2 days. The reason why it is so important is that in these cases, the machine is under a very high stress. Every day that goes by that a machine that is such severely imbalanced is shortening the life of the equipment. We know many different types of stresses. For example, this is a mechanical stress. There's also thermal stresses. For example, a motor that is working under high temperature for consistently or continuously for prolonged periods of times. Any mechanical engineer knows that this motor will not last as much. And the goal here is to find these issues early on, right? Whether it's with the cameras, whether it's here with vibration and tachometer and motor current, find these ones early on, fix these ones as fast as possible, and therefore really prolong the life of the equipment. Now, we're gonna touch on this one also from the business case side, but basically you understand that if I buy the same centrifuge and this centrifuge can now last dozens of percents, 30, 40% more time, and I'm able to replace less centrifuges on site, my maintenance costs and my labor costs are obviously lower. Spare part costs, obviously inventory, cash flow, and so on are heavily impacted because of this one. After they removed here the residue, going back to this use case, the system again looked at these specific frequencies and was able to confirm that the relevant frequencies went back to green, were back to normal, and the centrifuge is now back to green. And this was also obviously shown within the system itself. So you can see here how it went back to orange. It was quickly fixed, and literally 2 days after, it was already green. I also want to mention pumps. I'm not going to go into too much details there. We can also send the relevant case studies to whoever it is interested after this one. But comparing what can be done with regular vibration analysis and with a much more holistic fusion of more sensors like flow and pressures and obviously motor currents and tachometers, you can see here on the screen the difference. And the difference is not only in prevention of catastrophic failures that are causing eventually stoppage of the pump, but also in shortening, or in this case, prolonging the life of the pump. Because, for example, when cavitation happens to the pump, it puts the entire pump under high stress. All its, whether it's bearings and its frame itself, is under very high stress. And by finding this one earlier, which can be done by looking very simply at the pump curve, we're able to find this one. Many of these cavitation events will not be seen in the vibration, but will be seen in the operational sensors, meaning the flow and the pressure in the motor current. And by finding these ones, the pump would still operate, but now it will operate for a much, much longer periods of time. So you can see here on the screen that whether it's cavitation use cases or impeller wear or other performance issues like working below Q min or above Q max, all of these cannot be seen in regular vibration analysis. But when we actually combine vibration analysis together with the flow and pressure and the motor current and the tachometer, all of these can be for sure monitored on the spot. Pump incompatibility is actually also one of the diagnoses. We saw sites that put either oversized or undersized pumps that are not in accordance to the process parameters. And obviously, that is also inducing stress on the pump itself, and it's shortening the lifespan of the pump. Now, we've seen here some use cases, and I want to speak about the business case and how this one actually translates into tangible, obviously, not only operational, but also financial impacts. And we're speaking in this webinar about coal. So I've taken one of the CHPPs that we're monitoring, and in this slide, what you can see is a comparison between 2024, which is the year before we installed the system. We installed it really late in 2024, and 2025. And what you can see here are the criteria that we spoke about in the beginning that we're now measuring. So these are all site numbers that are obviously tweaked a bit to keep them anonymous. But basically, both looking at downtime hours, cost of spare parts and equipment, cost of the downtime itself, only in the places where there is no buffer, there are no stockpiles, and it directly translates to loss of revenue, labor cost, and obviously the total combined cost. And what you can see here, many times we're asked, what is the ROI? How quickly can I see ROI? What you see here is that over a 4-month period, when only half of the machines were covered, because it was still in a implementation process, we already saw savings of more than $1 million, which is obviously more than the entire cost of the system, So you can see here the downtime hours, which are more than 15 hours that were saved, cost of spare parts and the downtime itself and the labor. But now the site actually delivered the breakdown where every failure, every row here in the table is a different failure, and the KPIs of that specific failure. And what is amazing to see here is how different these KPIs are in different sections and different machines on the mine. For example, some machines, for example, here, that specific motor was part of the critical mine that delivered, of a critical pump, I'm sorry, that delivered 900 tons per hour. And they had a lubrication issue there that could not be seen by regular vibration systems. Our system with the sensor fusion was able to pick it up, and the site actually put a number on it, a bit more than an hour, 1.7 hours, not a dramatic number, but eventually it's a number that accumulates together with the rest of the failures that were found. And that number, it translates to downtime cost according to the site metrics and spare parts and so on. But what is more interesting to see here is that even equipment that was redundant, for example, these pumps did not have any impact on the downtime because there is redundancy. Once a pump is down, another pump just starts working automatically. And the metric here is they were replacing these pumps every 2 years. That was their policy. They've performed their reliability analysis there. They've analyzed the MTBFs and so on. And that was the policy of the site. After installing the system, they've seen that the pumps, after reaching 24 months, are actually still green because all of these factors that previously shortened the life of the pumps, whether it was severe imbalance or cavitation and other flow issues in the pump, all of these issues are now gone and the pump just lasts longer. And what a team on site does is, or did in this case, is they've taken the cost of the pump, they've divided it by how many months it used to, right? How many dollars does it take to operate that pump for a month? But now that pump is not replaced. In this case, that specific pump, pump 2304, lasted 5 months longer. That other pump 2303 lasted more than 9 months and it's still running. So they can now put a number of how much money these 9 months or 5 months were worth. And despite the fact that there is no downtime cost here, it does contribute pretty significantly to the reduction of the maintenance costs. So you can see here again, to sum up, how different KPIs, whether it's reduction of maintenance cost, prolonging of the life of because of the prolonging of the life of the equipment, or direct downtime costs, like we've seen in the run-of-mine conveyors or the plant conveyors because of rips and blockages, how they all eventually accumulate to a pretty significant number. This is site numbers, not our numbers, that in really 4 months' time, we're able to return not only the entire investment on the system, but even more than that. That's it from my side. I'll be happy to answer any questions from the audience regarding these ones.
Thank you, Michael. Those are extremely valuable insights there on DataMind AI and how it's helping with predictive maintenance on site. It is now time for the questions, and I will start with the first one I have here in front of me. Can you please explain how bearing fluting is specifically identified in the envelope demodulation trace? Can you show it to us?
Sure. So first of all, I'm not a vibration analyst myself, but if I go back here, when we actually look at the regular spectrum, From my understanding, obviously, we see here these high-frequency bands that are connected to deterioration of the bearing itself. But when we actually perform envelope demodulation, we see several phenomena. One is we see here the harmonics of the demodulated envelope itself. These harmonics increase the chances that we're looking here at fluting. Another thing is that in these envelope demodulation, there are also frequencies that are electrical frequencies, obviously the 50 hertz of the electricity itself, that very, very hard to see in the regular spectrum. Obviously, without even filtering noise, that would be even harder. So here, it's much easier to see, both looking at the electrical frequencies themselves and looking at the fact that there are harmonics of the demodulated bearing frequency. I hope, again, I'm not a vibration expert. We can also take it offline with a team that can provide an even more in-depth explanation.
Thank you, Michael. Next question. Is the focus of Raise Labs only in mining industries, or are there similar case studies and sensors for utilities, manufacturing, and the energy sector?
Sure, it's a very good question. So yes, we're working today with Siemens Energy, for example, in their power plants. The mining sector is by far our largest focus, but we are working today both with power plants, similar case studies regarding what they call the balance of plant, so critical pumps, fans, and compressors on site. These are parts of the site that when they stop, the turbine itself stops, and then there are outages. And we also work with oil refineries, again, similar case studies, like critical compressors, critical fans and pumps on their side. It's also worth saying that we have versions of the hardware that we deploy that is ATEX. So it is explosive, it's meant for explosive atmospheres like oil refineries and others. So the answer is yes.
Thank you, Michael. The next question is, what were the parts savings for the replaced pump in line item 3 of the cost savings?
Let me go back there. Can you repeat the question there again, please?
What were the parts savings for the replaced pump in line item 3 of the cost savings?
In row 3, so in row 3, we're looking here at pump 2501. And basically, we're looking here at 32,000. I hope I understood the question correctly. I'm not sure I understood it. So maybe to give a bit more context, when we look at saved parts, it's the ability to find failures earlier and to prevent the entire replacement of that machine. So for example, here, if I postpone replacement of the entire pump, obviously, this is how much I saved. If I lubricated the bearing and I prevented the loss of bearing, or in some motors, I need to replace the entire motor because the bearing itself cannot be replaced, this is the cost of that was prevented. So I'm able to really operate the same site with the same equipment and same productivity, but to reduce the amount of critical replacements that were done, and to therefore reduce the operational costs. I hope that I answered the question.
Thank you very much, Michael. Look, that's all the question time we have today. I'm sorry if we didn't get to your question. If we didn't, please send it through and we will forward it to the Raise Labs team to get an answer. I'd like to give a big thank you to Michael and Andrew for your time today. Your insights are appreciated as always. Just a reminder, we have recorded the presentation today and we will send you all a link to access the video through the OSMINE YouTube channel. Thank you to everyone who's attended, and we look forward to welcoming you to the next OSMINE webinar.
Thank you, Sam. It was a pleasure.
Thank you, Sam. Thank you, everyone.
Cheers.